Welcome back to our channel. Today we will see some more question and answers from alcohols, phenols and ethers lesson, class 12 chemistry, CBSE. So the next question which was asked several times is, describe the chemical test to distinguish between ethanol and phenol. So they asked a test to distinguish between ethanol and phenol. We need to find out a test to distinguish between ethanol and phenol. You know, there is one test called Iodoform test. So these alcohols which is having methyl groups, they can give methyl group or ethyl groups. They will give the Iodoform test. So this Iodoform test will be given by alcohols but not the phenols. So ethanol when warmed with NaOH and I2 gives yellow PPT, that is the Iodoform. So if you can take ethanol CH3 CH2 OH and react with NaOH I2 iodine, so then you will get iodoform, that is like chloroform. It is called CH, Cl3 is chloroform, here I3 iodoform. So this gives the iodoform. This is the precipitate, it is in yellow color. So whenever you get this yellow color precipitate, we can say that is ethanol. Phenol will not give this particular test. So CH3 CH2OH reacted with NaOH in I2, you will get a iodoform CHI3, yellow color precipitate. And the byproduct you can also write. Here there are several byproducts. HCOO, Na sodium salt of the corresponding acid, that is formic acid sodium salt, then sodium iodide NaI, and water H2O, and then if you take more number of NaOH molecules, you will also get NaOH as the byproduct. So these are the byproducts. But main test, since they asked to distinguish these two, you can say that when ethanol alcohol reacted with sodium hydroxide and I2, those are primary alcohols mostly. Reacted with I2, you will get yellow color precipitate. This is called iodoform test. Iodoform test. But when you react with phenols, it doesn't give this particular test. Using this, one can able to distinguish between ethanol and phenol. So this is one question. Next one. Next question is, addition of Grignard reagent to the carbonyl group of compound forming an adduct followed by hydrolysis. Explain the mechanism of this particular reaction. So Grignard reagent addition. Grignard's reagent addition. Grignard's reagent. This is alkyl magnesium halides are called Grignard reagent, RMGX. So this RMGX addition to a carbonyl compound further followed by hydrolysis. This is the thing they have given and asked to explain the mechanism. So you know the carbonyl compounds are like ketones or aldehydes. This is COO. Now I have RMGX. RMGX. What will happen in addition reaction? So the carbonyl compound, we need to see oxygen is more electronegative. So whenever the oxygen is more electronegative, the pi bonded electrons will move towards that. So it gets partial negative charge, carbon gets partial positive charge. Similarly here CMG bond, metal is mostly Mg. So R will be getting the negative, Mg is positive charge. So R minus Mg plus. So this you can add now negative to the positive and make positive center to the negative center. So R will come and attack to this particular carbon. So you are creating a new CC bond, carbon bond, and O it will get this one. So if you write this particular reaction, so what will happen? C, same, you can continue this. C, two bonds, and one bond is now R, newly R. Then single bond and O, then MgX, O minus, so MgX plus Mg and X, Mg and X, MgX. So this is the compound it forms. Here you have positive charge, correct? MgX. Once again, here it can break. This is minus, this is positive. So this is the addition first. So Grignard reagents add to the carbonyl compound. This is the addition. Now it undergoes the further hydrolysis, this particular one. So that is the second step they asked to explain. So this is called addition product. So addition product generally called an adduct. ADDUCT. So it is the adduct. In the second step, what will happen? In the second step, this adduct, that is C, R, two bonds, O, then MgX. This is the adduct what we have seen. So this adduct further undergoes hydrolysis. In presence of acid, that means water in presence of acid, this OMgX here. Water is H and OH. So H minus and OH plus and OH minus. So now here you know this is more electronegative, so minus. Metals are always electropositive, so get the positive. So this positive part add to the negative part of this addendum, adduct, and the negative part add to the positive part. So what will happen now? I will get C, R, and O, and H. So you get alcohol. We can obtain alcohol plus Mg, OH, and X. Hydroxy magnesium halide. Hydroxy OH will come to the Mg. One side is OH, other side X. Magnesium hydroxy halide. So this is the way Grignard reagent addition to the carbonyl compound leads to the formation of alcohols. So the question they asked is the mechanism of this particular reaction. What is that? Addition of Grignard reagent to the carbonyl group of a compound forming an adduct followed by hydrolysis. This is the question they asked, and we could able to explain this similar way. Okay, understood? I hope you understood. This is the carbonyl group, and carbonyl group O is more electronegative, so it gets negative charge because this pi electrons will move, and this gets positive charge. It is full negative and positive once it moves fully. And RMgX, metal carbon bond is there, carbon gets negative charge, metal is positive. You see, this is the case where carbon gets negative charge. Most of the case carbon will be a carbocation, it is a positive, but here it forms a carbanion. Carbon gets a negative charge, it is called carbanion because of the highly electropositive metal. So that's why my negative, this negative part will come. If you want to consider any reaction where CC bond newly formed is this particular reaction. Okay, so you will get the adduct, addition product of the alkyl magnesium halide with the carbonyl compound. Then the addition product undergoes hydrolysis like this, breaks up, and H plus is one side and OH minus other side, and you will get the alcohol. This is the one we will be need to understand. Clear? So next one we will try to see another question, and the IUPAC name of the particular compound. So IUPAC names, we will see one or two questions related to IUPAC names. IUPAC name of the following compound. So this is the compound given, and they have given here OH and here NO2, and another also NO2. So this is the way they have given, and they asked to write the IUPAC name. Whenever you want to write IUPAC name, we need to first take the functional group, major function. In this case, the major functional group is OH, so you can consider as phenol. But the phenol OH from onwards you need to number. Number can be started from this direction or this direction. You see, whenever you start this direction or this direction, whatever number comes. For example, if I start clockwise, 1, 2, 3, 4, 5, 6. So the substituents are second position and fifth position. That is, total substituent number is 2 plus 5, it equal to 7 in this case. If I do the numbering in reverse, 1, this is 2, this is 3, 4, 5, 6. In that case, the total number of the substituents numbering. So this is third and this is 6. 6 plus 3, 9. So 7 is lesser. So you consider this number instead of opposite. Clear? So better to consider this particular number. So what happened now? 2 position 1 nitro group and 5 position 1 nitro group. So 2, 5 dinitro. So you can write 2, 5 dinitro phenol. 2, 5 dinitro phenol. That is the way we can number the particular compound. So this is one way we can number it. So like this, whenever there is a phenol group, you better consider that as the major compound, then we can easily number them easily. And another question also asked is the boiling point of ethanol is higher than methoxymethane. Ethanol is higher than methoxymethane. Ethanol is CH3 CH2OH. Methoxymethane is the ether, correct? Methane is CH4, substituent is methoxy group. So this is the dimethyl ether. It is called methoxymethane or dimethyl ether. So they asked the boiling points. Boiling point of the boiling point of ethanol is higher than methoxymethane. So the boiling points are increasing. This is having more boiling point than this particular one. I think you can easily explain this particular one. Whenever you want to explain a boiling point or melting points, you need to see the associated molecules, whether there is any association is possible because of some bonding. Ethanol exists as associated molecules. So why? So I have CH3, CH2, then O and H. This is ethanol. Clear? Say CH2OH. If I take another ethanol molecule, HO, then CH2CH3. This is another ethanol. So whatever O gets some partial negative charge, H is positive charge, here partial positive and negative charge, and this where you have the bonding between these two. What is this type of bond is called? Hydrogen bond. What is that is called? Hydrogen bond. H bonding. So this is intermolecular hydrogen bonding. Because of intermolecular hydrogen bonding, all ethanol molecules in ethanol gets associated. So when they are getting associated, you need more energy to remove them each other. So that's why the boiling points are higher. So ethanol exists as an associated molecule due to the strong intermolecular hydrogen bonding. So therefore high energy is required to break these hydrogen bonds. Hence it has a higher boiling point than that of methoxymethane, which is not associated with such intermolecular bonding. Here I can't get any hydrogen bonding because you can see CH3O, CH3. Carbon oxygen electron negativity difference is very less. So they can't form really minus delta and plus delta and have it hydrogen bonding. So here you see the hydrogen bonding where the hydrogen is flanked by 2 electronegative atoms. That is the place we need to identify for hydrogen bonding. So ethanol molecules are associated in ethanol due to strong hydrogen bonding, but in methoxymethane ether that type of hydrogen bonds are not possible. So the boiling points of ethers are lesser when compared to the corresponding alcohols. So here methoxymethane will be having less boiling point than ether. So this is the reaction we have read in this case, and now we will see the. So far we have seen all alcohols and phenols. Now we will go for the last part of ethers. So ethers, first we need to understand some of the IUPAC names also, very important. So they asked to one IUPAC name of ether CH3O, C, CH3, CH3, CH3. You know the ethers ROR. These are the ethers ROR, ROR prime. Ethers generally we will write in common name di alkyl alkyl ether. Alkyl alkyl ether. If the alkyls are same, di alkyl ether. So like that. But IUPAC when it comes, IUPAC names, you have to write one as the substituent. One OR group as the substituent. OR group, R group is alkyl, OR group is alkoxy group. Alkoxy group. Correct? So this alkoxy alkane. So I have RH, it is alkane. If I replace this H, by OR, then I will get ROR. So this is ether. So I can consider this as a substituent. Substituent. So when you are considering this as a substituent containing alcohol. So this substituent is called alkoxy. So alkoxy alkane. Alkoxy alkanes are the IUPAC names for ethers. Alkoxy alkanes are the IUPAC names for ethers. So this particular one also we need to consider similarly. You need to give the naming similarly. So what I can write here? Clear? So if I have to give like this, what is the name for that particular compound? So you need to say the smallest one as the alkoxy group. Here this is the R and this is R prime, this particular one. So this you consider as alkoxy, the smallest one. Alkoxy. So that alkoxy is now what? Methoxy. So that is methoxy. This is methoxy. Now this is alkane. This alkane, how I can number? 1, longest chain I need to identify. 1, 2, 3 or 1, 2, 3. This is the longest chain. Longest chain is either this or either this. You can consider either. Both are 3. So the longest chain as per that it is propane. Clear? So I can write propane is the parent. Propane. In the propane there is a second position, there is another methyl. If I take this chain, then this is additional. So that is third, 3-methyl propane. Correct? 3-methyl. So I can write 3-methyl. 3-methyl propane. Clear? Then this need to be written as alkoxy. This is what position it is there? Second carbon. So 2 alkoxy is methyl, methoxy. 2-methoxy. 3-methyl propane. 2-methoxy. It is second position. Correct? This is second. Clear. 1, 2. Second position I have methyl group. Clear. So 2-methoxy, 2-methyl propane. That is the IUPAC name for that particular compound. So I will explain once again. Can you just see? If I have ROR prime, either this or this can be taken as alkoxy group. But which one we will take? Generally less number of carbon containing one is the alkoxy. So here 1 methyl, 1 carbon. So this is called as alkoxy. So you take this as a substituent. So I am writing the same compound like this. For example, I have like this 3 carbons. Now CH3. Here I have substituents. One is CH3, another is OCH3. Then CH3. You see this and this are same. CH3, then C, then CH3. And the substituent here CH3. Here are substituent. So now if you can take 1, 2, 3 numbering, and you can easily write that propane, 2-methyl, 2-methoxy. Correct? So methoxy first, 2-methoxy, 2-methyl propane. It is very, very simple concept. So like this we can write. Another example we will take and see. One more example. These are all previous year asked questions. So you just keep practice them. Another one is CH3, CH3, then CH2, O, CH2, CH3. So this is the compound it was given. So you can now identify what are the 2 alkyl groups. This is one alkyl group and this is another alkyl group. So this alkyl group you can add O because it's a smaller one. So you can write ethoxy. Ethoxy. Alkane. So this alkane containing how many carbons? That is the one we need to say. So 1, 2, 3 carbons, or you can put the numbering this way: 1, 2, 3. 3 carbons is the longest chain, so you can say it is a propane. It is propane. So at 2 position I have a methyl group, 2 methyl propane. But at 1 position I have oxy group. So 1 ethoxy, correct? First carbon I have ethoxy. So 1 ethoxy, 2, second position I have methyl, 2 methyl, 2 methyl, then the parent compound is propane. So you can write as propane. So this is the simplest way we can able to write it. Clear? So 1 ethoxy, 2 methyl propane. This is the reaction. This is the IUPAC name for this particular compound. Clear? Okay. So now we will see some more questions which were asked. Okay. So the next question: write the equation involved in the reaction Williamson's ether synthesis. Williamson's ether synthesis. This is one particular reaction where ethers can be prepared by using this reaction. Here alkyl halides are reacted with alkoxides. So generally alkyl halides will be reacted with the alkoxides. If you want same type of ethers, diethyl ether, then both are ethyl groups. You can take this R and that. Otherwise you can have different R, O and A. So this is the alkoxide, metal alkoxides, R, right? So then what is the ether you will get? I have this R together you will get. So R, O, R prime. Then NaX will go. So this and this was connected. So R, O, R prime, then NaX, then NaX. Clear? So this is the Williamson synthesis. So you have alkyl halide and sodium salt of another alcohol. You can take alcohol, RO, R prime, OH is called alcohol. You replace with sodium salt of that one. So sodium salt of sodium alkoxide, this is called, and alkyl halide. So alkyl halide reacted with sodium alkoxide, you will get the ethers. So if you want to get a same ether, both are R, like ethyl group, then you can also take here ethyl. So here I can take ethyl halide, so sodium ethoxide, then you will get diethyl ether. So this is the way we can see. For example, if I want to prepare differently, for example, CH3 methyl iodide can be reacted with sodium ethoxide, for example C2H5ONA. So I will get a reaction where this is the one. So CH3, then O, C2H5, O, C2H5. Simple. So you can take this and this particular one. O is the connecting part. So CH3O, C2H5, then NaI, then NaI. So this is the ethyl methyl ether. So this is the way we can write the reaction. If I want diethyl ether, so what should we do? You can replace this also ethyl, that is CH3, CH2. Then you will get CH3, CH2, O, CH2, CH3, that is CH2. So diethyl ether. So the famous commonly used ether is diethyl ether. This is the way Williamson synthesis will be used. Okay, this is one particular reaction asked, and it is very, very important. This Williamson synthesis mostly used for ethers preparation. So you can remember that alkyl halides are reacted with alkoxides, metal alkoxides. So then you will get it. Then another important reaction they asked to explain is acylation of anisole. What is anisole? Anisole is also a ether. Clear? Anisole, aromatic. Anisole, that is methoxybenzene. Methoxybenzene is anisole. OCH3 group. It is called anisole. This anisole will undergo acylation. They ask Friedel-Crafts acylation. Friedel-Crafts acylation. I hope you know these acylation reactions. Benzene you also would have done. Acylation is COCH3 group. Acyl group is COCH3 group. This is called acyl group. How we will done acetyl chloride, that is CH3COCl, or acetic anhydride CH3COO COCH3, that is we can take it. So CH3COCl, in terms of a, I need to get a carbocation, correct? All these are electrophilic substitution reactions. So for that you need to have anhydrous aluminum chloride. So anhydrous AlCl3. So this Cl3 will take Cl minus and AlCl4 minus, then carbon will get positive charge, that is CH3CO plus is the electrophile, that is CH3CO plus is the electrophile. Electrophile will come and substitute at these three positions. The possible positions are these three. Why? Because this oxygen is having lone pair of electrons, so it gives the electrons, so it is electron donating group. Once this gives the electrons, in the benzene I have 5 carbons. So in which carbon this electron density goes and sits, that is the carbon, more electrophiles can come and attack. So if you can write the resonance forms, for example one I can show you here. You see this carbon gets negative charge, and next this negative charge goes inside, then this comes here, this carbon gets negative charge, then this negative charge goes inside and this comes here, another form. So you see these 3 carbons, arrows where they are ending, those 3 carbons only gets the negative charge. That means the electrons given by O is mostly resides on these 3 positions. More electron density is there on these 3 carbons when compared to these 2. That's why the electrophile prefers to go these 3 places. So these 2 are ortho, either position is same, and this is para. So I will get both ortho and para products. So I can get ortho substituted anisole. So the products I will write here. Products. The products of the reaction is, one is OCH3. Here is the one. What will come? COCH3. C double bond O CH. This is the way we need to write. One product. Another product will be, this is ortho. Another will be para. OCH3 anisole, and here COCH3. You can write simply COCH3 or C double bond O CH3. Both are same. So this is the way we will get. The product is the minor and one will be the major. But this is major because it is having symmetric nature, but it is crowded near to each other, so it is minor product. That is okay. Minor, and this is major product. So more amount will be this and less amount will be this, but both are possible because the incoming electrophile position will be decided by the already existing substituent on the benzene ring. So this is there, so it will be done. And when compared to benzene, when anisole, whether having more reactivity towards electrophilic substitution or less reactivity, that also one question you can ask. And compared to benzene, plain benzene, if I take a benzene like this, I don't have any substituent, but it undergoes electrophilic substitution. This also undergoing electrophilic. You remember when compared to the benzene, anisole participates in this electrophilic substitution very fast. The reactivity of anisole is faster, higher than benzene, because here some more electron density is coming from the anisole. That means more number of electrons are available on benzene, such that electrophile easily can attack. So it is electron donating group. That's why the reactivity will be higher. Reactivity will be higher. That is one way we can also understand. Okay. And another question we will see. One more question we will see, then we can stop in this class. Ethers. So the reaction of ethoxybenzene with HBr, what will the product? Ethoxybenzene. Ethoxy OC2H5. This is ethoxybenzene. So ethoxybenzene, when it reacted with HBr, hydrochromic HBr. So when HBr it reacts, what is the compound? One we will be getting. So this ethoxybenzene is like OC2H5, and this is H plus and Br minus, here O minus C plus here. So the bond O and C, there is a bond CH2 CH3, correct? This is the so O minus C plus and H plus and Br minus. We can try to, yeah, this is the way it happens. So now for simple to understand, so now you break here and add H here and C2H5 Br, so you will get a phenol. Clear? You see I have this and OH, so OH is the phenol. The next is H C2H5 Br, C2H5 Br. So this is the way we will be, it will be converting. So ethoxybenzene, any alkoxybenzenes can be converted into phenols by reacting with HBr, This is the better way to remember this particular compound. Okay. Thank you. We will see in the next class question and answers. See you.